I forgot to do any posting of stuff on Friday, so I put it all up there now. Um, and now that I have everything in the morning, I'll get everything all done. I'll still have to do some work down here. But now that we're here, we're recording. Well, this is kind of working. So on Friday, we started talking about mole ratio, which is the ratio of moles in an equation. And we can do this in varying different ways. Atoms, molecules. We in chemistry think about a reaction in terms of moles, but we don't always necessarily have one. Sometimes we have half. If you're doing things on an industrial scale, you could have 10. The problem with moles is we can't measure them on a scale or anything like that. So we know we can convert between mass and moles. So if we can do this ratio and then we can add those steps, kind of like what we did here, but we're going to simplify all of this into one big thing. So Friday we generally just looked at doing some simple conversions. We looked at these two. We have all of these potential ratios. You're never going to write all of the ratios out. You're going to get a question. How many moles of oxygen are required to react with 14.8 moles of aluminum? 14.8 moles of aluminum. Whatever number you're given in the question, we do this. We want moles of oxygen. So this is just a one-step thing. I want moles of oxygen. I want to get rid of moles of aluminum. So we go back to this balanced equation. There's 3 moles of oxygen for every 4 moles of aluminum. Go away. And then we break out our handy dandy, well, Windows calculator. 14.8 times 3 divided by 4 equals 11.1 moles of oxygen. And that's the kind of fundamental stoichiometry step, going from moles of something to moles of something else. How we get moles, it can come from a varying amount of things. Mass is the most straightforward one because for ionic compounds and whatnot, we can weigh them. But if it's a gas, there is ways to do that. We have molar volume is 22.4 liters per mole at 0 degrees in atmospheric pressure. If you're not at that, we hopefully I'll be able to spend like a part of a day on what's called the ideal gas law that relates pressure, volume, temperature, and amount of stuff. If you're doing it in solution, there's a way, and we'll definitely get to solutions. So, I mean, that other one is this times 2 divided by 3. So the answer to that one would be, if you did it, 7.78 moles of oxygen. But I want the answer there should be 0.56 moles of aluminum oxide. So that's the mole conversion. We were doing this in class. You would have had time to do those things. Then we want to talk about gravimetric stoichiometry, and it's calculating masses. These problems we call them mass stoichiometry because we're converting mass of one thing to mass of another. We can do that with the periodic table because we have all of our molar masses. Um, and we're going to do this all kind of in one big long calculation. So let's determine the mass of carbon dioxide. So that's what we don't know. Produced by burning 1 kilogram of methane and oil. So we're going to do this in kind of a couple of oil in that sense. And this is why there's other considerations, but when we have fuels, the first thing we need is an equation. So we're burning methane in oxygen, producing carbon dioxide and water. So 1 and 1, 4 and 4, 2 plus 2 is 4. So that is a 2, that is a 1, that is a 1. So this one's fairly straightforward. Because we're looking at carbon dioxide and methane, I'm going to write it down now. Eventually, I stop 1 mole of methane produces as a ratio 1 mole of carbon dioxide, and that's our mole ratio. So when we do one of these, we're given a mass. We're going to convert mass to moles with the molar mass of whatever the first thing we're given. Then we're going to convert moles to moles using stoichiometry, the mole ratio. And then we're going to use a second molar mass. So in this question, we're talking about methane and carbon dioxide. So we need the molar masses of those two. And to save time, because I know what they both are because I'm a nerd, carbon is 12, oxygen is 1, and some change. And so we would have to add those up. When we do that next one with the C12H26, I don't know that off the top of my head. So it's the same idea. We're starting with, what does it say? A kilogram of methane. So 1,000 grams of CH4. Ultimately, way over here, we want grams of carbon dioxide. I don't know a way to go from one of those to another. So the first step in any chemical calculation is convert whatever you have to moles of methane. Well, we have grams of methane, and we know that that ratio or relationship is the molar mass. So 1 mole is 16.05 grams per mole. So that's my first step. If I look at units, and if I did that calculation like we did in chapter 12 or 13 or whatever it was, we would find out moles of carbon dioxide, or moles of methane. And just to go back to how we started it, that's that first step right there. But this is all long and convoluted and has some writing. And then we did the stuff about converting moles of one thing to moles of another. Well, if I fundamentally want grams of carbon dioxide, I can't convert moles of methane to moles of carbon dioxide, but I want to get rid of, whoops, yeah, well, we can do it that way. I don't want moles of methane. I want moles of carbon dioxide. And this is the actual stoichiometry step. And we had from our ratio, 1 mole of carbon dioxide comes from 1 mole of that, which makes this a little bit easier. So that cancels with that. So if we did all this calculation, we would have moles of carbon dioxide. Do we want moles of carbon dioxide? No, we want grams of carbon dioxide. So we're going to add a third step after our stoichiometry. Well, I don't want moles of CO2. I want grams of CO2. And well, we know 1 mole of this weighs 44.01 grams. So now if I go moles of that cancels with moles of that. So we have all of these things. The unit that's left over is the unit that we want. And this framework for mass-mass stoichiometry, 1 over the molar mass of whatever we're starting with. The mole ratio from the balanced equation. If you don't use the balanced equation, this step is wrong, and your answer is going to be wrong, even if those two are correct. And then we're going to take the molar mass of what we want. So this is where I think Mrs. Parley and I will set it up. We set these up the exact same way. You go on, this is how you set up a mole calculation. How you actually do the math is a little bit different because I'll show you quickly after we do the next one how I learn these. It's fundamentally the same thing. 1,000 grams. I do each thing separately. Well, but I kind of ignore the ones. I don't need to multiply by 1, but I divide by 16.05. I'm going to do it here times 1 divided by 1 because that's that step. And then the 44 is on the top. Multiply by that. So, well, I'm pointing with my finger. 1,000 divided by 16 times the numerator in the mole ratio divided by the denominator multiplied by that molar mass. And I push equals because I'm not super worried about significant figures. We get 2,742 grams of carbon dioxide, which is one of the reasons burning fossil fuels isn't so good. Um, just because it's here and it's a little bit simpler. When I did these in high school, we didn't use this kind of bracket framework. We did things with fractions. I think your book does something like this as well. Just to show you that it's out there. Everything's the same. Gram CH4 cancels, moles, moles. But this is how my teachers did it. Everything works the same. This is just a little bit more concise and for a lot of students nowadays is less intimidating because it's like, holy crap, there's 3 fractions. I don't know what to do. Well, the fractions are all there. So that's the first one we're going to look at today. We're adding a step at the beginning, adding a step at the end, and that's it. So I'm going to do this one, and then we'll wait and do a little bit more. You can try a couple. Burning some sort of oil, C12H26. Normally, like on a test, I'm going to give you a balanced equation. So 12 and 12, because I noticed something, 26. 24 and 24 are 48, and 26, 14, 74. Oh, half of 74, half of 70 is 35, 37. So our mole ratio now is 2 moles of, whoops, gives us, we're starting with the same mass, so it's a little bit different in one sense, but in terms of most people can't tell the difference that 1,000 grams of that and 1,000 grams of methane contain vastly different amounts of things. C12H26. We want grams of carbon dioxide. So it's the same framework. I don't want grams, so get rid of it. That was a really big 6. $12.01 times 12 plus. So this one has a molar mass of that's still 44.01 grams per mole. So 170 point. Okay, I've got moles of this. I don't want moles of that. I want moles of carbon dioxide. Well, 24 of those, 2 of those. Could you simplify that? Sure. Don't. Added stuff causes, if you forget to divide 1 by 2, everything goes bananas. I'm also looking for that number. Moles CO2. Well, I don't want moles, I want grams. CO2, 1 mole weighs 44.01. So now we bring out, again, our handy dandy calculator. 1,000 divided by 170.38. That's a significantly smaller number of moles, but 1 mole, 5 moles of that gives us a significantly times 24 divided by 2, and then multiply by 44.01. So 3,000, well, 3,100 grams of carbon dioxide. Is that more? Well, 2,700 versus 3,100. If you're burning 1,000 grams of a fuel, which is better for the environment, this is one of the reasons why they say the smaller things like natural gas are better than heavy fuels. You also technically get, it has to do with the energy that comes out, which you talk about in Chemistry 12. But that is kind of our starting point. Which fuel produces the least amount of carbon dioxide per gram? That's CH2. Other considerations. Ease of storage, safety of storage, ease of obtaining. Why is natural gas a little bit trickier? Because it's more in the gas state, which is harder to transport, harder to do stuff with. Liquid oils are easy. You can put them in a truck or on a train, which still isn't the safest, but that's the way our whole economy is done. Um, and I'm not saying we should be using fossil fuels at all, um, but this is just one consideration why, if you're heating your house with oil and you could potentially convert it to natural gas, well, you're saving the environment a little bit. You're still going to need to burn stuff. I mean, if you can, but there's all sorts of other considerations in here. This isn't just oh, this one makes less carbon dioxide. There's another one, price. So these are our steps. Write a complete balanced equation for the chemical reaction. I tend to underline the 2 things that are in the problem. I have 1,000 grams of oil, mass of carbon dioxide. So we know that's what we're looking at. Write the molar masses under them. So if I was doing it like in this sense, we said the molar mass is and we're given 1,000 grams of this. and we want to find grams of that. That's usually just to help you because there's a lot of people over a lot of years have made the mistake of they know how to do the stoichiometry, but find that mass. It's like, well, I'm not asking you for that mass. Write the appropriate information, use dimensional analysis. If you've taken physics, you've heard this term. It's a unit conversion. Grams over, so if this is A, 1 mole of A over grams of A. Mole B over your mole ratio. Grams, whoa. The molar mass, and then you're going to get your answer. So instead of rushing through, if you want to, I'll write the equation for this. Iron and copper 2 sulfate oh, let's for fun call this iron 3 sulfate plus copper 3, 2, 3. If you start with 10 grams of iron, how much copper would you produce? And then we'll go through a couple more. If you want to try that today, you can. But we'll go through a couple of examples tomorrow. I may do some of those as well. I think I've got answers for a lot of them. We'll talk about that, but because we still at this point, I have no idea when we're done. In our staff meeting last week, the 2 dates that were being bantered around are the 5th of June, which would be your traditional last day of classes, or the 12th, which I think was the end of exams, and then that was grad week, and I think that's when those were the 2 dates that I vaguely remember. But other than the fact that I can't assign a whole pile of stuff, we're actually covering some things. So we'll talk about limiting reagent and yield, and that's kind of the end of chapter 12. And then I think, oh no, I put an assignment up for this, didn't I? Or for chapter 11. But that's where I was going to stop today. Does that sound good? Any questions?
Sounds good.
All right.
Yep.
I guess I will see a couple of you in a half an hour. See ya.
Bye.
Thanks.